Hello students, in today's video we will discuss about moment of inertia, radius of gyration, then rolling motion of a body. What is moment of inertia? You might have already heard of inertia. You know inertia what it is because we already learned in different classes. Inertia is an inability of a body to change its state of rest or of uniform motion until an external force is acting on it. Now, what is moment of inertia? Moment of inertia is the same effect on rotating objects. It's a quantity expressing a body's tendency to resist angular acceleration. It is the sum of the product of the mass of each particle in the body with the square of its distance from the axis of rotation. For example, if we have an axis of rotation like this and body is over here, and you have a mass point at this point, let us imagine it is at a distance uh, from this axis at a distance r, and this mass point be m. So what is moment of inertia? I is equal to mr square. Now let us imagine we have many particles like this, m1, m2, m3, like that. Each one of it is at a different distance. M1 is at a distance r1, M2 is at a distance of R2, M3 is at a distance of R3, like that. In that case, what we do is I will be M1 R1 square plus M2 R2 square plus M3 R3 square. If there are n particles, this same terms should be increased to n terms. So I in that case will be equal to sigma I equal to 1 to n mi ri square. Now, how will we usually express moment of inertia is I is equal to mr square. So where m is the mass of the body and r is the distance of the axis from that mass point. Unit of moment of inertia is kilogram meter square. Its dimension is ml square. Now, the rotational analog of mass for linear motion is moment of inertia. So wherever mass, because you know that inertia is, mass is a measure of inertia, normal inertia, linear inertia is measure. How will we express its mass looking at the body's mass? If the body's mass is higher, we say the inertia is more. Mass is less means inertia is less. That is for linear motion. Uh, the same effect the moment of inertia gives in rotation. If moment of inertia is high, that means its rotation will be less. If moment of inertia is less, the rotation will be more. When we learn about rotational motion and system of particles, especially their rotational motion, it is very important to know what is meant by radius of gyration. Radius of gyration is nothing but it is a distance from the center of mass of the body to the axis of rotation. It is the distance of the center of mass from the axis of rotation of a body. So we can express moment of inertia in terms of this radius of gyration as I is equal to mk square. So k is equal to root I by m, we get, and its unit is meter and its dimension is L. Now each of these bodies, when they rotate about their axis, some kind of axis, when they rotate about, they have different values of moment of inertia. For example, a ring perpendicular to the plane, if the axis is perpendicular to the plane of the ring, then the moment of inertia is mr square. How will we find the radius of gyration of the ring? Mr square has to be equated to mk square. So k will be equal to r. Similarly, a thin rod perpendicular to the road at midpoint is the axis lying. In that case, its moment of inertia is ml square by 12. Similar method of calculation of k, if you use, k will be equal to L by root 12. In the case of circular disc, if the axis is perpendicular to the disc at center, it will be mr square by 2. moment of inertia is mr square by 2. Again, k is equal to r by root. Hollow cylinder rotates about the axis of the cylinder. Then moment of inertia is mr square, or k is equal to r. Solid cylinder, on the other hand, if it is rotating on the axis of cylinder, it will be mr square by 2. In case solid sphere, if it is rotating about its diameter, the moment of inertia is 2 by 5 mr square. And each of these bodies, like ring, circular disc, hollow cylinder, solid cylinder, if we take the axis, not the central axis, but the axis is through the diameter, then each of these values will be divided by 2. For example, a ring's rotation is about the diameter of the ring, then its moment of inertia will be mr square by 2. In the circular disc case, if the axis is the diameter axis, then it will be mr square by 4. Hollow cylinder, on the same way, like axis is the diameter, then mr square by 2. Solid cylinder, axis of rotation is the diameter axis, then mr square by 4, like this. So whatever central axis values we get in these objects, that we have to divide by 2 for getting the diameter axis. That is how we can easily remember the values. In translational motion, we have learned equations such as v equal to v0 plus at, where v is the final velocity, v0 is the initial velocity, a is acceleration, and t is the time. Second equation of kinematics is x equal to x0 plus v0 t plus half at square. And v square is equal to v0 square plus 2ax, where x and x0 are the initial final position and the initial position. V and v0 are the final velocity and the initial velocities. So their analog equations in rotational motion, that is known as the kinematics of rotational motion. In that, what we can write is this v has to be replaced by its analog quantity in rotation, which is known as omega. V0 will be replaced by omega naught. A will be replaced by alpha. Similarly, position in linear motion has to be replaced in rotational motion by angular displacements. So the angular position is theta, final angular position theta, initial angular position theta 0. Then initial velocity is omega 0. Alpha is the angular acceleration. Similarly, over here also we have to take x. X is the displacement in linear motion, meaning x minus x0. Actually 2a x minus x0 it is, which will be replaced by theta minus theta 0, which is called the angular displacement. So these are the kinematic equations in rotational motion. Omega equal to omega 0 plus alpha t. Theta minus theta 0 is equal to omega 0 t plus half alpha t square. Omega square minus omega 0 square is 2 alpha theta minus theta 0. Now we will learn rolling motion in brief. Rolling motion means it's a kind of motion in which there is rotation and linear motion. It's a mix of rotational motion and translational motion. So the motion of a rolling wheel, if you take, is the sum of the translational motion of the center of mass plus the rotational motion of the wheel around the center of mass. You can see in this figure two velocity vectors here will give a zero velocity at the bottom. Similarly, the bottom of the wheel is at rest even for rotation. See here, this is linear motion, its velocity is in this direction v, and when it is rotating the same point, at the same point there is a minus v velocity. So when these two movements are constituted together to make a rolling motion, then what happens is this v and minus v get cancelled and v equal to 0 we get. But on the other hand, here this is v, this is also v, center of mass v only, so 2 v's we will get. So this point will have more speed, this point will be almost at rest. So when we talk about the kinetic energy of rolling motion, we have to think about its two types of motion, that kinetic energy of translation and kinetic energy of rotation. Kinetic energy of translation, for us it is very familiar. It is half mv square. And kinetic energy of rotation is half I omega square. The mass is replaced by moment of inertia and linear velocity is replaced by angular velocity. For a body, ICOM is equal to mk square we studied, where k is the radius of gyration. So we can rewrite our equation, this first equation over here. We can replace and substitute the respective values, like omega is v by r. Omega is equal to v by r and I is equal to mk square in a general expression. Then it is E is equal to half mv square plus half mk square in place of I, and v square by r square in place of omega square. So when we take the common factors outside, that is common factor is half mv square, it becomes like this, half mv square into 1 plus k square by r square. Next important topic in the chapter is conservation of angular momentum. Angular momentum, as we all know, it is L is equal to I omega, and if there is no external torque acting on the system, since you know torque we learned already, it is dl by dt. So if torque external is absent, it's 0, that means dl by dt will be 0 and L is a constant. So L, we know that L is I omega. So this I omega will be a constant in case if torque is absent. So here in this example, we can see that if L equal to I omega is a constant, means in this example of this girl rotating by spreading her hands, stretching her hands on either side, what is happening is the R value is increasing. This is her axis of rotation. From there, the value of R, the distance to the mass points, this distance is increasing. So what happens? mr square will increase. So I is obviously I is increasing. When mr square increases, I increases. So omega has to decrease such that the product I into omega remains a constant. That means if this value is increasing, this value has to decrease by the same order so that L will be a constant. Look at this picture. In this, she is keeping her hands near to her axis of rotation. See, the axis of rotation is this and her mass points are like this. So the distance is very less in this case. So what happened is I is equal to mr square also decreased. So when I equal to mr square decreases, omega will increase. So what happens is her spindling speed will increase. She will rotate with large speed. But here what we can say is she is moving with a small rotational speed. Omega is small here. So that means her rotational speed is less. Here her rotational speed will be greater because of the I value is less.